Now, application 3, the adjacent graph, shows the variation of the speed as a function of time for an object that was originally at rest. At t equals 0 seconds, it began to move in the positive direction along a straight path. During what time is the object speeding up? We can see that the graph of v versus t shows two phases or two variations, increasing then decreasing. So speeding up means that the speed is increasing from t equals 0 seconds till t equals 4 seconds. And speeding down from t equals 4 seconds till t equals 8 seconds. Now, at what instant or instance is the object moving at a speed of 10 meters per second? In order to determine the instance at which the object moves at t equals 10 meters per second, we have to draw a virtual horizontal line at v equals 10. And the point at which this line, or the points at which this line intersects with the graph, are the points that we're looking for. So we can see that there are two instants at which the object is moving at a speed of 10 meters per second. It's at t equal 2 seconds in the first phase, and at t equals 6 seconds in the first phase, the speed is 10 meters per second. Now calculate using the graph the accelerations during each of the two phases of motion. In the first phase, again, A average is delta V over delta T, V final minus V initial over T final minus T initial. The final state is B in this phase, and the initial one is A. So VB minus VA over TB minus TA. 20 minus 0, the unit is meter per second, over 4 minus 0, the unit is second. So we have meter per second over second is meter per second squared, and the value is 20 over 4, 5. So it's positive 5, showing positive acceleration because the speed is increasing. However, in the second phase, again, upon applying the same rule, Vc minus Vb, the final state now is C, not B. So Vc minus Vb over Tc minus Tb. It's 0 minus 20 meter per second over 8 minus 4 seconds. So now we have minus 20 over 4. It's minus 5 meter per second squared. And this negative acceleration is expected because the speed is decreasing. Now, application 4. Suppose you bike down a long steep hill. At the top of the hill, your speed is 0 meter per second. Then as you start down the hill, your speed increases. Each second, you move at a greater speed and travel a greater distance than the second before. So this means that you're speeding up. So each second, each same interval of time, the distance covered by you is increasing. So this is just like the case that we studied about the girl. So during the 5 seconds it takes you to reach the bottom of the hill, you are an accelerating object. The data in the table below show how your speed changes during each second of your bike ride. So we have at t equals 0, speed is 0 meter per second, t1 2 meter per second, t2 4 meter per second, and so on. Use this data to plot the line graph that represents the variation of the speed as a function of time. So we have to represent the speed on the y-axis and the time on the x-axis. And the scale is, it's clear that we're counting by 1 for time. So every 1 centimeter is 1 second for the time axis. And as for the speed, we are counting by 2. So every 1 centimeter is 2 meters per second. So this is an easy graph. You plot each point. We have first 0, 0, 0, 0. Then the second one at t equal 1, the speed is 2, so this is the second point. At t equal 2, it is 4, so this is the third point. At t equal 3, it's 6 seconds. So these are the points obtained when you join them. Don't forget also to write the title, the variation of the speed of the bike as a function of time. Now calculate the slope of this line graph. What does the slope represent? The slope represents the acceleration. So in order to calculate the slope, we need to divide the rise by the run. The rise is delta V by the run is delta T. So it's VA minus VB over TA minus TB, 8 meter per second minus 4 meter per second over 4 second minus 2 second, it's 2 meter per second squared. So because the unit is meter per second squared of the slope, so the slope represents the average acceleration of the bike. Now use the data to plot a line graph that represents the variation of the distance as a function of time. So this table shows the variation of the distance as a function of time. 0, 1, 4, 9, 16, 25. The distance is increasing but not in the same manner like the speed did. So when we have a constant rate of increase or constant rate of decrease, we expect the graph to be a straight line. However, as for the distance versus time, the distance is not increasing by the same rate. So we do not expect it to be a straight line. Plotting the points, taking a convenient scale every 1 centimeter 1 second on the time axis and every 1 centimeter 5 meter on the y-axis for the distance. We plot each point here, 2, 4, 3, 9, and so on. In order to know how to label the points here, we have to divide the given value by the scale. So 1 divided by 5 is 0.2, so you go 0.2 centimeter. 4 divided by 5, this is 0.8. So you go 0.8 centimeter and label 4 here and so on. Showing, of course, on the axis the physical parameter with the unit, and here the physical parameter with the unit, and the title to the variation of the distance covered by the point as a function of time. So this is a parabola. You're not supposed to join the points using the ruler here. You have to use your hands only because this is not a straight line. So do not join every 2 successive points by a ruler. Just draw them all together using your hand in order to obtain a parabola. Now describe the variation of the distance covered with respect to time. Does it vary uniformly? Explain. The distance increases with time. The distance first increases by 1 meter per second. Here you can see that it increased by 1 meter during this second, then 3 meters during the other second. Then it increased from 4 to 9 by 5 meters per second, 7 meters per second, and 9 meters per second. Now, summing up the graphical representation, in order to study the motion of an object moving in one direction in one dimension along a straight line, we need to study the variation of its position or distance, speed, and acceleration as a function of time. So here we have, if the sum of the acceleration is positive, then the graph of x versus t, or of d, we can say either x is the position, d is the distance. So I want you only to concentrate on the distance now. So it should be an increasing parabola. For the negative, it's going to be also an increasing parabola, but in this shape, taking this shape. The graph of v versus t for positive acceleration is an increasing straight line. For negative acceleration is a decreasing straight line. And the graph for a versus t is a horizontal line. Now we can calculate in this case when the acceleration is constant and the object is moving along a straight line. We can calculate the distance. Forget about this one here. I don't want you to memorize it. Just concentrate on the distance equal half at squared plus v initial t. We calculate the distance covered by the object, knowing its acceleration after a certain time and knowing the initial speed. And v is also equal to at plus vi. We can calculate the speed of the object at a certain instant, knowing its acceleration and its initial speed.